Thank you for the introduction from our session chair. So I am Zi Chen, and I'm from University of Maryland, Baltimore County. And today I will present our recent work, Parallel Inclusive Communication for Connecting Heterogeneous IoT Devices at the Edge. This is a joint work with my colleague Yan Xin Yao and Dr. Yan Chao Zhang from Arizona State University and my advisor, Dr. Ting Zhu. So let's first take a look at the background of this project. Actually, we are witnessing the exponentially increasing number of Internet of Things. This figure shows the previous few years and the growth, the trend of the future. The y-axis is the number of IoT devices. As of now, we can see it's around like 25 or 30 million IoT devices around us. And we can expect exponentially increasing, and it will reach around 80 billions in 2025. So, however, the wireless spectrum used to accommodate these devices are very limited. It's never growing, right? So the different protocols need to share the spectrum, especially on the ISM band. Here's an example. In the 2.4 gigahertz ISM band, the Wi-Fi devices share with Bluetooth, share with Zigbee, share with some of the video devices like the baby monitor. So if you look at this figure, the number of Wi-Fi devices is increasing as well. The same story to the Bluetooth. It will reach like 800 million in 2022. Think about that in a smart home scenario. We already have so many wireless devices using Wi-Fi and Bluetooth technologies. For example, we have For example, we have Wi-Fi video streaming devices. We have a Bluetooth headphone. We have a Wi-Fi connected laptop. We have a Bluetooth connected keyboard. We have video surveillance video cameras by using Wi-Fi. We have Bluetooth smartwatch and so many more. Nevertheless, the developing of new type of devices keeps going. Here comes the problem. How can we deal with the huge number of IoT devices in spectrum crisis? How to coordinate heterogeneous devices together for better networking performance? So we propose PIC. PIC stands for Parallel Inclusive Communication. Specifically, in this paper, we propose how a PIC device communicate with a Wi-Fi device and a Bluetooth device in parallel. And we also do the inverse way from Wi-Fi and another Bluetooth talk to the gateway. So let's first take a look at the existing approach if a gateway wants to transmit to a Wi-Fi and a Bluetooth device. The gateway has a Wi-Fi radio, which talks to Wi-Fi device. It also has a Bluetooth radio, talks to the Bluetooth device. But these two transmissions should either in different time slots or in different frequency slots. If they want to transmit at the same time, we'll see the collision. So in our solution, our PIC gateway actually enable transmission one piece of signal, and this piece of signal, let's say a packet. This packet will include both the Wi-Fi and the BLE messages, and these messages can be received by a Wi-Fi and a Bluetooth devices. Note that these two pieces of message are totally independent, and they can be totally different. So, by solving the collision problem, we can get a lot of benefits from PIC. In the Wi-Fi and the BLE coexistent scenarios, we can have a higher throughput. We know that with higher throughput, we can support more applications. And we can have low delays. For some critical applications, delay is very important, like the fire alarm system or heart attack monitoring. And we can also have a lower energy consumption because with less collision, we need less retransmissions. And we know that the energy consumption is very important to low power Bluetooth devices. Okay, I will first introduce the system structure of our PIC. It is divided into downlink and uplink. For downlink, our PIC has a very unique Wi-Fi and Bluetooth symbol mapper. This mapper takes the input of the Wi-Fi signal as well as the input of the Bluetooth signal. Within this mapper, we combine these two signals together and feed the combined signal to the RF front end. The front end transmits the signal, and the signal can be picked up and demodulated by the Wi-Fi and the Bluetooth devices. In uplink, the Bluetooth device and the Wi-Fi device transmit their signal, and the signal will combine in the air. The RF front end pick up the combined signal and feed into an oversampling and FFT module. By using a faster than usual FFT, we can actually extract the Bluetooth signal by looking into details on Bluetooth affected Wi-Fi subcarriers. We can also compensate Wi-Fi signal, and finally we will have the Wi-Fi data and Bluetooth data. So for sake of time in this talk, I will only introduce the downlink part. Before jumping into our design, let's review some basic things related to Wi-Fi and Bluetooth. So Bluetooth uses a frequency-based modulation scheme. Assuming the device wants to transmit 1011, and for the first one, it will transmit a very fast frequency in a time domain. And if we look at the frequency domain, the frequency is a little bit higher. We usually call it a Mach frequency. And when it transmits a 0, it uses a relatively low sine wave, and this is called a space frequency. And the same thing for the next two one, we will have another two Mach frequencies. So we will also take a look at the relationship between a Wi-Fi channel and a Bluetooth channel. The green part is a Wi-Fi channel. It can be like 20 megahertz or 40 megahertz. Within one Wi-Fi channel, we actually have multiple Bluetooth channels. We will take the first channel as an example. And within one Bluetooth channel, we have multiple Wi-Fi subcarriers. Remember, Wi-Fi use OFDM modulation scheme, so they divided the whole 20 megahertz or 40 megahertz into pieces, and these are the subcarriers. And as the aforementioned space and the mark frequencies, they are overlapped with some of the Wi-Fi subcarriers. So this is the basics of our work. And here comes the basic idea. If we want to transmit, if we want to embed Bluetooth data into Wi-Fi signal, what should we do? For example, if we want to embed a 0, we want to manipulate a little bit of the subcarrier overlapped with the space frequency, as well low down a little bit on the mark, so we can get a 0 at the Bluetooth side. And if we want to transmit or we want to embed a 1, we do the inverse way. It's very simple, but it's very challenging. The main challenge here is how to embed Bluetooth data without changing Wi-Fi data. Remember, our goal here is to transmit Wi-Fi and Bluetooth signal in parallel. We shouldn't destroy Wi-Fi data after putting in Bluetooth data. We note that Bluetooth use frequency-based modulation scheme, as I described above. And Wi-Fi uses phase and amplitude-based modulation scheme. Since Bluetooth does not care about the phase, so we only need to deal with amplitude part. To resolve the amplitude problem, we utilize and observe the fact that Wi-Fi and Bluetooth modulate data on totally different time scales. That is, the symbol duration of Wi-Fi is 4 times longer than a Bluetooth symbol duration. Now I will introduce the core design of our Wi-Fi and Bluetooth symbol mapper. If you remember, this is the main part of our PIC device. Let's first take a look if a PIC transmits a specific Wi-Fi data, what will happen at the Bluetooth receiver side. So we take a look at we take the quadrature part component at the subcarrier M and S as an example. The subcarrier M and S are overlapped with the Bluetooth mark and space frequency, respectively. Let's say this period equals to 1 Wi-Fi symbol duration. So if the PIC device transmits a -1 in this one Wi-Fi symbol, the Wi-Fi receiver will get a -1, no problem. And on the subcarrier S, if we transmit a 1, the Wi-Fi receiver will get a 1 as well. But at the BLE side, remember because BLE is much faster, right? So it's 4 times faster. So this whole Wi-Fi symbol duration is divided into 4 pieces. It gets a positive value because Bluetooth only care about the amplitude. It doesn't, the phases, it doesn't matter. So we can actually get two similar value on the mark and the space frequency, and which result invalid value when demodulating. So to transmit a valid Bluetooth data, instead of transmitting the same data during a Wi-Fi symbol, we chop the whole symbol into 4 pieces. And if we transmit a sequence like this way, we will still get the same -1 at a Wi-Fi receiver, because remember the Wi-Fi receiver process the whole the signal in a whole Wi-Fi symbol duration. But at the Bluetooth side, we will get this pattern. And the same thing to the subcarrier S. We transmit a specific sequence. At our Wi-Fi receiver side, we still get a 1, but at the Bluetooth receiver side, we get this pattern. And by comparing the signal strength on mark and the space frequency, we get a negative, positive, negative, positive pattern, and this can be demodulated into 0, 1, 0, 1.
Did you call about the mic?
I'm sorry.
Help with the mic?
We also have other challenges in this paper, like how we disentangle the Wi-Fi and the Bluetooth signal in uplink, and how to compensate Wi-Fi signal in uplink, as well as a synchrony problem between Wi-Fi and the Bluetooth. For the detail, please refer to our paper. Here, for implementation, we implement a PIC device in a USRP B210, and we use a laptop and a CC2560 as Wi-Fi and Bluetooth devices. We implemented 3 baselines to compare with PIC. The first one is a dual radio gateway. This is an existing solution. The other one are pure Wi-Fi to Wi-Fi communication and pure Bluetooth to Bluetooth communication, which means in pure Wi-Fi to Wi-Fi, there is no interference from Bluetooth. And we also have the oracle, which is a theoretical upper bound of fully concurrent transmission. That means there is no noise, no channel fading, just in stereo. To extensively evaluate PIC, we vary modulation scheme, coding scheme, Wi-Fi bandwidth, Wi-Fi, Bluetooth packet size, distance, a number of devices, and the transmission power. 4 scenarios are used to evaluate our system directly in line of sight. Directly in line of sight and non-line of sight. Human moving in the middle, and human carry the Bluetooth devices and working. Okay, here's the most important result. The throughput versus the number of Bluetooth devices. So you can see when the number is increasing, the blue line is the dual radio approach is decreasing because of the more and more collision occur. But for our PIC, it's like keep constant and very close to the oracle. Oracle is, remember, is the performance in theory. And for the throughput of a Bluetooth device is for PIC is keep going because the number is increasing. But for dual radio is like going up, but get down later. Again, it's because of the collision. And we also have a benefit in terms of a delay. This figure shows the delay, the round trip delay. We can see our system keeps stable while the dual radio gateway keeps going up. The same thing to the energy consumption. Our system has a much lower energy consumption compared with dual radio gateway because so here the energy part is evaluated on the Bluetooth devices because to Bluetooth the energy consumption is important. Okay, PIC is actually inspired by a body of prior work like the mitigating interference with the same technology or among different technologies. Our system also related to cross-technology communication. In comparison to those work, PIC enables parallel and inclusive communication among heterogeneous IoT protocols. It achieves much higher throughput, lower delay, lower energy consumption in Wi-Fi and BLE coexistence scenarios. Furthermore, we can also extend PIC to other protocols. We expect to extend PIC between Zigbee and Bluetooth, as well as LoRa LTE Zigbee. As long as they are on the same frequencies, they're working on the same frequencies, it's possible to do that. Another thing is we can transfer PIC to different versions of OFDM-based Wi-Fi and Bluetooth standards, including the latest Bluetooth 5.0. To conclude, we designed the PIC, the first parallel inclusive communication technique that enables parallel bidirectional transmission of both Wi-Fi and Bluetooth data at the same time within the same channel. The parallel inclusive communication concept is generic and opens a new door for more efficient communication in the shared wireless spectrum. PIC reduces the round-trip delay time and energy consumption by a factor of 5, 90, and 50 respectively. Thank you.